What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video I'm going to talk about finding limits of piecewise functions, just like the piecewise function shown here. And we could think of piecewise functions as being defined in pieces, hence the name, right? The outputs of this function, or the y values, are given by two different expressions here. For x values less than or equal to 1, we're going to plug those x values into x minus 2. That's going to give us the y values. For x values greater than 1, those y values are given by x squared. So with these functions, they have the potential to have jumps in their graphs at these breakpoints. That's what I like to call this number 1, this breakpoint where the function changes from being defined by one thing to another thing. We could potentially have jumps. That's why to find limits, we need to check the left and the right limits and make sure they're equal. We can't just do direct substitution with these piecewise function examples. So let's jump, pun intended, right into this first example. Again, we're looking at that same function we saw on the first screen. And again, we can't just plug 1 into this function. Why not? Well, let's think about what this function looks like here. So this is an x-axis. That's when x equals 1. Let's see. For x values less than or equal to 1, the y values are given by x minus 2. So I'm going to write that to the left because less than or equal to, that's to the left. Greater than 1, or to the right of 1, those y values are given by x squared, right? Here's the reason why we can't just plug 1 into this function, because we plug 1 in and we're going to get the y value 1 minus 2, so that's negative 1. We know that because that's where the or equals to is. But we could have a situation like this where we know that the function is defined as a line, x minus 2, to the left of 1. And we know at 1, the y value is negative 1. So we have like something like this. But from the right, we could have a situation like this where we have a hole and the function does something like this, right? We could have a situation like this. We have to check the right limit. Plugging 1 in doesn't tell us anything about the limit. So we have to check the right limit because we could have a situation like this where the limit doesn't exist. Or we could have one like this. What would it look like for the limit to exist? And that's from the right-hand side. This hole would have to pick up exactly where that filled-in hole is, where that function is defined. The hole would have to pick up there, and the function would have to continue something like that. So we're trying to check which of those cases we have. Do we have the jump, or do we have it like filled in, connected? We can approach from the left and from the right. So how do we think about that? Again, I love this model, drawing this out, drawing 1, because then it clearly shows us how to find the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. And this is our strategy for finding limits of piecewise functions at these breakpoints, which is typically what we're asked to do as x approaches the breakpoint here. Is that we're going to check the left and right limits, and if they're the same, then that's the limit, and if they're not, then it's DNE, and it's that simple. So how do we check the left limit? We look at this expression we wrote on the left. Remember, this is how the function is defined when x is less than or equal to 1. So we plug 1 in this expression, we get negative 1. And how do we know that's the limit from the left? Well, this is a line. Again, it's a line, and it ends at the y value negative 1. So when we approach from the left, the y values get closer to negative 1. The limit from the right's a little trickier, right? When we plug 1 into the expression on the right, 1 squared, that's 1. How do we know that's the limit? Because maybe you're thinking, well, wait a minute, the function isn't defined as x squared when x equals 1. It's defined as x minus 2. That's okay. What this gives us is the y value of this hole, right? This hole coming from the right. And so we're finding the y value of that hole, and we're trying to see, does it line up with the y value from the other side? If it does, the limit exists. And in this case, if it doesn't, then we can write does not exist, DNE. That means there is a jump. From the left, we end at negative 1, like this. From the right, we pick back up at 1, and so it looks something like this. And in fact, I'll actually show you the graph to just support this DNE for this example when x equals 1. There's a jump here. We check the limit from the left and from the right. They were not equal. Hopefully this method's making sense. We're going to practice a few more examples. So let's go and try this example. Again, we're finding the limit as x approaches this breakpoint, which in this case is negative 2. And I always like to write this out. What does this function look like? To the left of negative 2, the y values are given by x squared minus 5. And to the right of negative 2, the y values are given by 7 plus 4x. How am I figuring this out? Well, I'm looking at these inequalities here. When x is less than or equal to negative 2, that's to the left on the number line, less than or equal. right? Greater than negative 2, that's to the right. So we're trying to figure out, do these line up at negative 2 and connect, or is there a jump? And we can do that by plugging negative 2 in to each of these expressions. So the limit as x approaches negative 2 from the left, I'm going to get that by plugging in negative 2 to this expression on the left, right? So negative 2 squared is 4. 4 minus 5 is negative 1. Boom. That's the limit from the left. So now I'm going to compare that to the limit as x approaches negative 2 from the right. I'm going to compare that. And I'm going to get that from this expression I wrote on the right. That's what the function is defined by when x is greater than negative 2. So when I plug negative 2 to that expression, I get what? 4 times negative 2 is negative 8. 7 plus negative 8 is negative 1. So that whole, right, on the right side connects exactly at the same y value as the curve on the left-hand side where it's filled in, it picks back up. We can trace from the left, from the right. In either case, the y values are approaching negative 1, and that's the limit. And we can see this from the graph of the function. Boom. Each side pops exactly into place. We can approach from the left and from the right. In either case, the y values get closer to negative 1, and that's the limit. All right, if you feel like you're getting the hang of this, pause the video. Try this example on your own. Press play. Use my work to check your work. All right, so the limit as x approaches this breakpoint, which in this case is 1, it's defined as negative x squared plus 5 when x is greater than 1. So I'm going to write that on the right. And maybe you don't have to write this number line business. Maybe you're like, look, I can look at the inequalities, I can think about this, do it in my head. Totally fine. I want to do this to support your understanding. I could see a teacher giving a problem like just a one-sided limit because they want to test, do you know what is on the left and what is on the right, right? So that's why I'm writing all this stuff out. So the limit from the left, this time I'm just going to write the word left to save time with the notation, and the limit from the right. Again, just going to write the word right. So from the left, again, using this expression here, plugging 1 in, negative 4 times 1 is negative 4 plus 10, that is positive 6. And from the right, I'm plugging 1 into this right-hand expression. We have to be careful. Order of operations. 1 squared is 1, then I make it negative. So negative 1 plus 5, which is positive 4. If this had parentheses, then you would do negative 1 squared, positive 1. Then it would actually work. The limit would exist because you'd get 6. So I think that's what this example is maybe checking. Are you going to make that silly algebra error there? So left is 6, right is 4. Limit does not exist. And we could support this again by looking at the graph and confirming that's in fact the case. There's a jump at 1. Next example, if you didn't pause last time, pause now. Try this on your own. And I love including an example like this because the function is not defined at negative 2, right? So I really wanted to show an example like this just to highlight, again, the concept of a limit is what's happening to the y values as x gets closer to negative 2. We don't care what happens at negative 2. We could have a situation like this where there's a hole, the function's undefined at negative 2, but the limit still exists. We can approach from each side. We could have the function be defined somewhere else, right? Like way up here. Totally fine. The limit still exists. It's still the same thing. It's the y value of this hole. We could also have it filled in. Those are like some of the examples we've already seen, right? We don't care what happens at negative 2. So not having that or equals to there, we really don't care about it. We just want to figure out how do we find the limit from the left, and that's from this expression here, and how do we find the limit from the right, and that's from this expression here. So from the left, I'm plugging negative 2 in to this left-hand expression. Negative 2 times negative 2 is 4. It's going to become plus 4. So negative 2 plus 4 is positive 2. And then from the right, how do I find the limit from the right? I'm plugging negative 2 in here. Negative 2 squared is positive 4. 4 times negative 2 is negative 8. Plus 2 is positive 2. Those numbers are the same. The limit exists and equals 2. And we can see the graph. There's going to be a hole where x equals negative 2. And the y value of that hole is going to be 2. Boom. When x equals negative 2, there's a hole. We just found the y value of that hole. It's 2. That's the limit. Awesome. All right, I think this is our last example. Let's go ahead and try it. As x approaches negative 3, this time it is from the left. Remember I said a teacher might ask something like this, right? They want to test your understanding. Do you know how to differentiate between coming from the left, coming from the right. So which of these functions gives us from the left? Well, that's when x is less than or equal to -3. So all we care about is this expression here. What happens when we plug -3 into this expression here? Well, I get -3, which is 3, minus 7, which is -4, and boom, we are done. We don't need to check the right-hand limit because we're not being asked about the right-hand limit or the two-sided limit, just a limit from one side. So this is why it's important to be able to sort of coordinate between these different inequalities, figure out what's on the left, what's on the right, and that sort of thing. Awesome. All right, we can again look at the graph of this. The limit from the left, we found it to be -4. If we were asked to find the general limit, it would not exist. It's a great example of make sure you read the problem. Read what it's asking you to find. Don't overcomplicate it. Don't make silly mistakes. Hopefully this video helped. Comment with any questions. If you liked the video, then like the video and subscribe. But most importantly, keep flexing those brain muscles, and I'll see you on the next video.